Yeah. So hi everyone. So in this lecture, we will try to look at intuitively how to analyze second order circuits. I'll take examples of second order circuits, but what I'm going to discuss in this lecture will apply even for higher order circuits as well. Okay. So to do that, I'll first very briefly discuss first order system, just to quickly refresh your memory and draw some conclusions. Okay, what you already know from first order systems. So one thing that I've shown here, this is a simple first order RC filter. You know, the transfer function for the circuit is 1 by 1 plus S by omega P or SRC. And the pole is at omega P is at 1 by RC. And so this will be your transfer function for this. Now I'll consider another circuit, which I haven't drawn the details of the circuit, but let's call it an integrator. So an integrator is a function with a transfer function like this. The pole will be at DC. In case of a first order system, the pole need not be at DC. Okay, it will be in the left of S plane. So again, just to clarify, all the discussions that I'm going to discuss in this lecture, all the topics that I'm going to discuss in this lecture, we'll assume they're all stable systems. So this is a given condition. So all the systems that I'm going to discuss are stable, which means all the poles will be in the left of S plane. Okay, or at max, it's going to be at the origin. So this here is an integrator with a transfer function 1 by SRC. Now we'll try to plot the frequency response of both these first order system and an integrator. So how is it going to look like? A first order system, the DC gain is 1 or 0 decibel. So normally we use Bode plots to plot transfer functions. So we take 20 log of the magnitude of the transfer function. So 1 means it's 0 dB. And after the pole onwards, the transfer function starts rolling off. In absolute terms, it rolls off at a rate of 1 over f, right? So if you take 20 log of 1 over f, it will roll off at the rate of minus 20 decibels per decade. For every 10x increase in frequency, you should expect a 20 dB reduction in amplitude. So that's the first order response. The difference between an integrator and a first order system comes at DC. For an integrator, the DC gain is infinity. Okay, the DC gain of an integrator is infinity. DC gain, or the word that I will use, is steady state gain. So these are all systems with which will have a transient output. So we will look at two kinds of behaviors when we talk about a system, but I'll come to that. But let me just complete the discussion. An integrator here has an infinite gain at DC. So if you substitute S equal to 0, you'll see that it's an infinite gain system. So that's where the difference is. At DC, it looks very different compared to a first order system. But the moment you reach the pole, after that pole frequency, which is 1 by RC, the integrator and the first order system are indistinguishable. They both look exactly the same. Okay, so here if you see, this is the high frequency response. This is the low frequency response. They both look very different at lower frequencies, but at high frequencies, they both look exactly the same. Okay, so now just to quickly refresh your memory, if you are to plot the response of a system, generally what we will be interested in is what is the transient response. So suddenly you excite the system, you suddenly feed an impulse to the system, or you feed a step input to the system, or you can even feed a ramp input to the system. At the origin, if you see, all these three functions have discontinuities, which means there is a sudden change. An impulse is a huge change at origin. A step input is a finite change, but it's still a sudden change. A ramp input, even though it's continuous, its slope is discontinuous. If you differentiate the function, the slope will be 0 and suddenly it will be a step function. So because slope is discontinuous, these are all discontinuous functions. Anytime a function has a discontinuity, which means there is a sudden change, you should expect infinite frequencies to be present. I mean, you should expect, if you take its Fourier transform, it will have some finite energy at very high frequencies. If you have watched some of my lectures initially, why does a sudden step correspond to infinite frequency? let's start with the basics. You take a sinusoidal signal with a frequency, say omega naught. Let the amplitude of the sinusoid be A. If you differentiate the sinusoid, what am I going to get? Let's assume the sinusoid is A sine omega naught t. If you differentiate this, you will get A cos omega naught t. Okay, A cos omega, into omega naught. So this is the derivative of this function. So now if you see, the slope of the function is varying with time. The maximum value of the slope will be simply A times omega naught. And that occurs at t equal to 0, right? Cos x is maximum at t equal to 0. So this is the point where sinusoid has the maximum slope. And that maximum slope depends on the frequency of the sinusoid. And that should make sense because let's say I'll keep the amplitude constant and I'm going to double my frequency. So you should expect one full cycle within one half cycle of the previous sinusoid. So it means now you can see the function is increasing faster. So I'll keep on increasing the frequency. At one point, when the frequency is infinity, it's going to look like this. It's going to look like the y-axis. So that at that instant, it looks like a step function. So that's what I mean. When you have a sudden change, for the system that's going to feel this input, or for the system that you're going to feed this input, at the instant where you're applying, the system will interpret it as a sinusoid of infinite frequency. So to predict the behavior of the system, what is the system going to produce as an output? What you have to look is, you'll have to look at the frequency response and see what is the behavior at omega equal to infinity, right? And you guys already know what frequency response is. It contains everything you need to know about the system. It contains information about the system for how the system behaves for different frequencies. Okay, so if you're applying a sudden change, you should look at the high frequency range of your frequency response. You should look at this region and try and predict its behavior. Then if the input, most of these inputs, if you see, right, if you see an impulse or a step or a ramp, for long times they have settled down. They reach a steady state behavior. They don't change much in the steady state. So which means they reach a DC behavior. Even if you look at a step function, it is constant. Constant means no change, right? So that's like a sinusoid of zero frequency. Even a impulse function, you look at in the steady state, its impulse is zero in the steady state, which means there is no change. Okay, and you look at ramp function, even though the ramp is changing, it depends on the slope, but the second derivative is zero. Only the first derivative is finite. Okay, and even the first derivative is not changing. So all these responses in the steady state, they all become low frequency inputs. So to predict the behavior of the system in the steady state, you will look at the behavior at omega equal to 0. Okay, on a Bode plot. So from the frequency response plot or a Bode plot, you can predict how the system is going to behave when you suddenly apply a transient input, step, impulse, ramp. Or if you want to predict the steady state behavior, what its output is going to be, you can predict it from the frequency response graph itself. So if I can just throw you a frequency response graph and roughly tell you how the high frequency and DC response looks like, you can with good accuracy predict what will be the initial or a transient behavior of the system and the steady state behavior. So keep this point in mind. We will be using this point to analyze all the circuits. Okay, so to suddenly analyze the steady state, the transient behavior, you look at the infinite frequency or the high frequency behavior. And to predict the steady state behavior, you look at the DC characteristics. So we'll start with a first order system and an integrator. The first order system, I'm going to feed a sudden step input. A sudden step means it's like an infinite frequency input. Now, immediately, the frequency response, it's a first order system. If you are to look at this frequency response and predict its behavior, what will you say? How does it look like? The transfer function looks like that of an integrator, right? Its integrator is also the same as a first order low pass filter. So all I need to do is with the integrating time constant of 1 by RC. So if I feed a sudden step input at t equal to 0, immediately after I've fed this input, you should expect the output to behave like an integrator. So integral of a step will be a ramp. Okay, at t equal to 0, if you zoom in this region and look at this behavior, it's going to look like a ramp function. So now we know the step response for a first order system is like this. It's going to start initially at 0 and eventually it's going to reach the steady state value. Now what we predicted is that we said that initially when you apply the step, it's going to look like t. It's proportional to t. Integral of step is ramp, right? So it's t. To be exact, if you look at this response, it looks like an integrator of frequency of transfer function 1 by SRC. So if you feed a step to this, you should expect t into RC, or if I'll call it t by tau. Tau equals RC. Now, this system, we know the exact response. The exact response is 1 minus e power minus t upon tau, right, into u of t. If you have done any basic first order circuit analysis, if you feed a step input to a first order RC circuit, the output should be 1 minus e power minus t upon tau. Okay. Now, if you expand it for small values of t, expand exponential function, this will be approximately 1 minus x. So this will reduce to 1 minus t upon tau, so which is equal to t by tau. So we predicted this behavior even before having an exact expression. Okay, so we already predicted this. We said, okay, it's going to behave like an integrator. Let's just integrate this step. You get ramp, and we predicted its output. The next step is the steady state behavior. Steady state is constant. The input now is a unit step function. So the DC amplitude is 1. The steady state, if you see, it looks like a DC input to the system, right? It's been 1 for a very long time. So the system will treat it like a DC input. So if the input is 1 in the steady state, you look at the transfer function, the DC gain is 1 or 0 decibels or 1. So which means the input DC and output DC are the same, right? So you directly say output is supposed to be 1. That's it. So steady state, you just say first order output is going to be 1. So that's it. We predicted this output. Now first order system is very simple. So we can directly derive closed form expression. So we didn't have to do this integration and steady state. But you will see later, when you complicate the system, when you add more and more poles, this comes in very handy. Okay, so that's something to keep in mind. Now I've shown here how does an integrator behave. Generally, if you feed an impulse to an integrator, the output of an integrator is going to be a step function. If you feed a step function to an integrator, the output will be a ramp function. Integral of step is ramp. If you feed a ramp function to an integrator, the output should be a parabolic output. Okay, output will be parabolic, right? So if you know the integrator transfer function, you can exactly predict what will be the slopes and all that, but just keep this in mind. Impulse to step 1 integration, step to ramp, there is 1 integration. Ramp to parabolic function, there is another integration. Okay, so I just discussed this function. So now again, I'm feeding an impulse to a first order RC circuit. If you're supposed to predict its input, you already know the first order transfer function looks like this. At very high frequencies, it looks like an integrator. So suddenly when I'm applying an impulse, this system will realize or think that it's an infinite frequency has been applied to it. So it's going to integrate it. So integral of impulse is a step function. So suddenly you see a step change at the output here. Okay, we can exactly predict what will be the step change also. If you look at the 1 by SRC transfer function at high frequencies, transfer function just reduces to 1 by SRC, right? This term becomes much greater than 1, so I can ignore 1. So if you feed an impulse to this transfer function, you will get an output of 1 by RC times u of t, right? Or 1 by tau times u of t at t equal to 0. So understand this is not the response for all time. It's just behavior at t equal to 0. So at this point, I have predicted it's going to be 1 by tau into u of t, just at t equal to 0. Now in the steady state, if you look at this, the input has become 0, right? There is no impulse input. So at t equal to infinity, there is no signal present. So if this input is 0 in the steady state, output should also be 0 because DC gain is 1. Input DC and output DC are same. So therefore, output also goes to 0. It's a first order system. We know it starts at 1 by tau and eventually it goes to 0. So you can just draw the response with the knowledge how to draw waveforms for first order systems. Right? I've already discussed this before, so I'm not going there. I'd recommend you watch the initial lectures on how to analyze first order RC circuits. Okay, but here the point I'm driving home is how to draw the response from the how to predict the output from the frequency response graph. Now I've slightly complicated the system. What I've done, I've taken a first order system, put a voltage buffer. So what does a voltage buffer do? It doesn't draw any current. It transfers the same voltage at this point to this point at the output. Okay, and at the output, I have cascaded it with another 1 by RC, another RC low pass filter. Now I want you to tell me roughly what will be the initial and the steady state behavior of this system, this RC cascaded system to a impulse input. Right? I'm suddenly feeding an impulse. You know, a first order RC circuit is going to behave like an integrator, right? At high frequency, this transfer function is going to look like this. And then you will predict, okay, this node, it's going to be a step. And you can even predict the value of the step. We just did it before. It's going to be T upon tau. Sorry, 1 by tau times U of T. I just wrote it some time back here. Its output is going to be a step when you apply impulse. Now you're applying a sudden step input to this RC circuit. This is a voltage buffer. The same step will translate to this point as well. And the value will be 1 by tau. If you feed the same step here, this circuit, RC circuit, is going to think that another infinite frequency sinusoid is being fed. So it will start integrating it. The output of this integrator is going to be a ramp. Again, we can write what will be the ramp output. It's going to be 1 by tau is the input into the system is 1 by SRC. So in time domain, it's going to be 1 by RC into integral of the input. So it will be 1 by tau times T. So the output you should expect is T by tau square. So you fed an impulse at T equal to 0, the output is a ramp. Okay, and if you plot the exact response, I'll come to how to plot the exact response a little later. Okay, you can see that the function here, it will reduce to something like T into e power minus T by tau minus 1. There is some factor and all that. And you can clearly show that that function will reduce to this. But you didn't have to know the exact solution, right? Here, by just knowing the frequency response behavior at f equal to infinity or omega equal to infinity, we were able to predict its transient behavior at t equal to 0. Similarly, at t equal to infinity, impulse input at t equal to infinity, its value is 0. So if I feed a 0 input here, we know the first order RC circuit DC gain is 0. So eventually you should expect this output to go to 0. Output will go to 0 in the steady state. So same way, because this steady state input is 0, this output will also go to 0. So what you know now is initially it starts off as, if I don't know this response, it starts off as T, like a ramp function, and eventually it goes to 0. Eventually it has gone to 0. So this is how the response looks like. So naturally you should expect, okay, if it's going to produce an all positive output, somewhere it should have reached the peak and it would then go back to 0. The function should look something like this. So this is what you could do by just looking at the frequency response. So you could predict the initial behavior and the steady state, or the final or the steady state behavior. So let's draw the frequency response of this system. It's a 1 by RC cascaded with 1 by RC. So the transfer function is 1 by 1 plus SRC the whole square. So if I plot its frequency response, the first order system will look like this. After the pole 1 by RC, it's going to roll off as 1 by SRC, right? Like a first order integrator. If you add another pole, then that's going to roll off with a slope faster than the first order system. That's going to roll off with a slope of 1 by SRC the whole square. Or in decibels, this is going to roll off with the slope of minus 20 decibels per decade. This guy, because it has two poles, it's going to roll off with a slope of minus 40 decibels per decade. Now, if you look at the steady state, the frequency response at f equal to infinity, it looks like a cascade of two integrators. Two poles, two integrators. Okay, so that's what I've drawn here. This is the behavior of the frequency response. The one shown in green is the frequency response of two integrators in cascade. That exactly matches with the two poles response at higher frequencies. Okay, so if you have a two pole system at very high frequencies, it's going to look like a cascade of two integrators. This is the thing that you need to remember very well. If you keep this in mind, then you can predict the behavior of two pole systems to sudden transient inputs. So I said impulse. If I feed an impulse, it's going to be output will be ramp, because impulse, when you integrate it twice, you get ramp. So what happens when I feed a step input? If I feed a step input, I should expect t square at the output. Two integrators, right? One, you integrate step once, you get ramp. You integrate ramp once, you get a parabolic output. So that's what you should expect to see. If I feed a step input to the system, let's not worry about the exact response. If I feed a step input to the system, at t equal to 0, I should expect a ramp output. A parabolic output. And what happens in the steady state? In the steady state, the DC gain of the system is still 1. You look at this graph, it's still 1. So therefore, if the input is 1, you should expect the output should also be equal to 1. So output is also 1, but somehow it reaches that 1 output. The exact way how it reaches, we will look at it later. But what you know is the initial behavior and the steady state behavior. You know these two behaviors. So roughly you can say, okay, it's going to start here, and you know the shape, how it's going to start. And you also know steady state, how it's going to look like. That shape depends upon the input shape, because the DC gain is 1. If the input is flat, output is also going to be flat. So you know this is how the function is going to look like. Now it can reach this position in different ways. It can reach like this, or it can reach a peak and reach like this. We don't care about that. Right now I'm focusing on the initial and the steady state responses. So extending the same way, okay, I've just drawn the response for step here. You can now predict what will be the behavior of a circuit like this. Let me just, because now that I've discussed the cascade of two poles, let's say I have n poles. I have cascaded RC and then put a buffer here, and then cascaded another RC, put a buffer, and so on. I've cascaded many such sections. Let's say I've cascaded n such sections. Then if I draw the frequency response, it's going to look like this. DC gain is 1. The steady state response is going to be, the steady state behavior is going to look like n integrators in cascade. This response is going to be 1 by SRC the whole power n integrators in cascade. So if I feed a step input here, say 0 to 1, and I ask you what is the output going to be at the output of the nth low pass filter, you will tell me just integrate this input n times. So if you integrate this function n times, you should expect first output is going to be t, second output is going to be t square, nth output is going to be t power n by n factorial or something. Okay, so what I'm trying to tell you is the shape is going to be an nth order ramp function, or a t power n, right? It's an nth order time domain polynomial. So that's the shape of this function at t equal to 0, or for sudden transients. So it's going to start like this. with a much slower slope. Remember, the n derivative of this function will be 0 at t equal to 0. So if you differentiate this function n minus 1 times, it's going to be 0 at t equal to 0. In the steady state, because the DC gain is still 1, right? It's cascade of RC, RC, RC sections. DC gain is 1. So you should expect the output to have reached 1. Okay. And it might reach the output any which way. So it will reach this output this way. But initially it will start off as, it might go this way as well. So initially it will start off with a slope, a function that looks like this, t power n by n factorial. Let's not worry about that second factor constant, but it's going to be proportional to t power n. Okay, so that's what I wanted to discuss in today's lecture. So keeping this in mind, you should be able to draw how the responses will look like for this filter, for a system that looks like this. You have a first order RC circuit followed by a unity gain amplifier and a first order high pass filter. It's also a first order system, but a high pass filter. So now I'm feeding a step input here, and I'm asking you to plot, guess what will be the output at t equal to 0. So you can think yourself, okay, it's a first order RC filter. So this output is going to be like a ramp, right? One-time integrator, first order RC circuit behaves like an integrator at t equal to at f equal to infinity. So this is like an infinite frequency. A step can be interpreted like an infinite frequency input. So it's going to behave like a ramp. So you know that it is t by tau. Now what about this circuit? High pass filter. A high pass filter has a transfer function of SRC by 1 plus SRC. Now if you plot SRC by 1 plus SRC, you have a 0 at DC. You have a 0 at DC. On a log scale, 0 will be like minus infinity, right? So you take 20 log of 0, that will be minus infinity. And I think you guys know this. So think about it this way. 20 log of 0.1 will be minus 20. 20 log of 0.01 will be minus 40, and so on. So when you reach 0, you will become more and more negative and reach minus infinity. So a 0 on a log scale, on a Bode plot, will be at minus infinity. So it will start from minus infinity. And then once you reach this pole at 1 by RC, you can ignore the 1 here. So SRC by 1 plus SRC. You can ignore the 1 here. So SRC and SRC will cancel out. You will get 1. So at high frequencies, it's a high pass filter. So the gain will be 1 or 0 decibels. So what happens here at infinite frequencies, it just passes the input as it is. So if I feed a ramp input at this point, I should expect the output to be the same ramp. So at t equal to 0, I should expect the same output at this node. Okay, so I fed a step input for this system, but the output has, remember this is a second order system because it has 2 poles. But the steady state behavior, the transient behavior at t equal to 0 looks like a system with just one integrator. Does that make sense? Yeah, if we can draw the overall frequency response, 1 by 1 plus SRC multiplied by SRC by 1 plus SRC. This transfer function will have a 0 at DC, so it's not drawn to scale here. So this is like, it has a 0 at DC, so it comes from minus infinity, right? And at 1 by RC, that's where the pole is. This guy gives you a pole, but the one pole here cancels out this 0. And you're left with only one more pole. So the Bode plot for this response, initially it starts off as a 0. At 1 by SRC, you get 2 poles. You get 2 poles at 1 by RC. But out of those 2 poles, 1 pole is cancelled by the 0 at DC. Right? That 0 is still present and that cancels out the pole. And what you're left with after that is just a single pole response. So at high frequencies, it looks like a first order integrator, a first order integrator. That's why when I fed a step input to the system, by looking at the frequency response, I can say the step output is going to be a ramp, because at high frequencies, it looks like a first order integrator. Only one integration takes place. Now, if I ask you what will be the steady state behavior, the input steady state is 1. It's a DC input. Now look at this here. The input steady state is a differentiator. At DC, it looks like a differentiated function, right? The differentiator transfer function is SRC. It's going to be at DC, it will be 0, and it will just blow up to infinity at omega equal to infinity. So in the steady state, it's going to look like a differentiator. Okay, so if you differentiate a step input, what do you get? You get 0 in the steady state. Sorry, differentiate a step input in the steady state, you get 0. That's it. I just looked at the frequency response and I told you exactly how the response is going to be at t equal to 0, the initial transient, and the steady state. Steady state is also going to be 0 here. Okay, so that's the power of frequency response. So that's why I said second order systems, or any higher order systems, you can predict a lot of its behavior by just looking at the frequency response graph. Okay, you can predict what happens at the initial transient event, and you can also predict what happens in the steady state, which is what we did in the system. Now, if you go through the lectures I posted initially, you'll say, okay, why to go through this trouble? I know how capacitors behave and capacitors and resistors behave. Using that, I can draw the waveforms. Yes, you can do that. So capacitor acts like a short circuit at high frequencies. So this node will be close to 0, and this capacitor acts like a short circuit. So if this node is close to 0, this node will also be at 0. So you can immediately say, okay, yes, it starts at 0. Okay, input starts at 0. But this frequency response gives you a little bit more information. Okay, it tells you the shape of the waveform also at t equal to 0. I'm able to tell you how it's going to look like. Okay, without having to derive a complexity. This is a second order differential equation. I have to solve it and find the solution. What if I make the system more and more complicated? Okay, then I need to know the exact equation to give you how the shape is going to look like. But what you are saying now is you don't need to do that. Let's look at the frequency response and compare it to some known transfer functions like integrators and differentiators, and then we can use them to predict its output. Okay, so that's what we are doing here. So you can even steady state behavior, capacitors are open circuit. So from that also you can say the output will be 0. But what I can say from the transfer function is that I can say from the transfer function, I can say that the derivative of the output is going to be 0 in the steady state. That's what I'll be able to say. And the steady state, it will be simply, the output will simply be derivative of the input. That is an extra information. I won't be able to say that by just shorting or open circuiting the capacitors. Okay, that helps me predicting the precise values, right? What is the initial value and what is the final value? You can predict that. But the shape of the waveform, some characteristics of those waveform, I can't get that information by just using capacitors as short and open, right? With that, I can't give that information. For that, I can give that information by looking at the frequency response. Okay, I can do something in circuit design itself. I can say, okay, the impedance of the capacitor has become so small that this node is almost close to 0. So the current drawn by the circuit will be VI by R. That flows into an impedance of value 1 by SC. So the voltage at this node will be VI by SRC, which is nothing but an integrator. I can do this as well. But if the circuit is too complicated, or if you are given the transfer the frequency response, you can predict it as well. Okay, whatever suits you. Fine. So that's how we predict behavior of higher order systems by looking at the frequency response. I can say what is the initial and the steady state responses. Now, the same way for this circuit, which we had analyzed a few moments back, we will see what happens when I feed a step input. Now, sorry, the circuit is slightly different. I have cascaded two high-pass filters. Okay, two first-order high-pass filters. So the transfer function is SRC by 1 plus SRC and SRC by 1 plus SRC. If you draw the overall response, it's going to look like this. It's going to behave like a second-order derivative, second-order differentiator for low frequencies because it's SRC the whole square. And when you encounter the pole, when you encounter 1 by RC, there are two poles at 1 by RC, and both of them will cancel out the two zeros. So the response will be 1 and or 0 decibels. So at high frequencies, the gain is just 1. So now I'm feeding a step input. I'm giving you this transfer function. Can you predict the output? You will tell me that, okay, at high frequencies, the DC gain is, the gain is just 1. So if I suddenly feed a step, I should expect a step at the output as well. Okay, I should expect a step at the output as well. Okay, and the magnitude of the step is going to be 1. The magnitude of the step is going to be just equal to 1 at high frequencies. The next thing is what happens in the steady state. Input is constant. Your input here is constant. Because my input is constant, in the steady state, it's going to behave like a second order differentiator. You have to differentiate the input 2 times. That you know that by looking at the response here. It's SRC the whole square. So if you look at this waveform in the steady state, it's going to be a second order derivative of the input. So if I feed a ramp step input, the output here is going to be 0 because if the first order derivative of a step itself is 0. So output will be 0. Now you can tell me what will happen if I feed a ramp input. If I feed a ramp input, because this output in the steady state is second or 2 times derivative of the input, or it's input differentiated twice, again it will be 0. Even if I feed a ramp input, the steady state output is going to be 0 here. Because if you differentiate ramp once, you get step. Differentiate ramp twice, you end up getting 0, right? It's a derivative of a step, which is 0. Now, if I feed a parabolic input, t square, then you know that this output is going to be a constant, right? Differentiate it twice. You differentiate this function twice, you're going to get a constant value. So that's the power of what I discussed now. By looking at frequency response, you can predict its shape, how it's going to look like. You know that because it's going to behave like a second order differentiator in the steady state, if I feed a parabolic input, I should expect a constant output. Anything before that, whether it's a ramp or a step, if you differentiate it twice, it's going to be 0. So you should expect a 0 output in the steady state. Okay, so now you can easily say, even if I feed a ramp input at the initial transient event, because its gain is 1 at high frequencies, it's going to look like the same ramp input. So I can easily say it's going to look like the ramp t. It's proportional to t. Steady state, again, it's going to go to 0. So it's going to have some behavior, let's not worry about the shape. It's going to go to some value and go back to 0 again. Similarly, when I feed a parabolic input, I should expect it's a high pass filter, right? So DC gain is 1 at, the gain is 1 at high frequencies, which means at t equal to 0, if input is parabolic, output is also parabolic because the gain is just 1. Steady state, it's going to be a step value. So it's going to reach the step value somehow. Okay, so that's how this behavior, this waveform shape is going to look like. I can derive the exact response, but I just wanted to give you this idea that intuitively you can guess the behavior of the system by understanding how its frequency response is going to look like. Okay, so that's the power of this approach. So this is what I wanted to discuss today. So I'll stop the lecture at this point. I'll open it up for discussions. The next lecture, I'll go into a rigorous mathematical treatment of second order systems. In case if it's too mathematical for you, I will make a video and upload it. Okay, so I'll stop recording at this point.